All right, welcome everyone to this week's webinar. I am Paul Lefevre, the Xojo Developer Evangelist. And this week, our webinar topic is designing delightful databases. Excuse me. This is a repeat of a database session from last month whose recording didn't come out quite so nice. So we're redoing it. There is a little bit of new content in this webinar. So if you were at the other one, you might want to keep this on in the background. And before we start, though, I want to remind everyone that Xojo 2014 release 2.1 was made available today. So if you haven't already, head on over to xojo.com and download that. And also today we announced the new London data center for our Xojo cloud service, which should be very, very useful to those of you in Europe. So I just wanted to point those two things out for everyone. And I want to remind everyone also to feel free and ask questions while I'm talking. I will look over and see them and address them when I can. So let's get started here. This webinar is primarily a keynote presentation, but we never know. It may drop into Xojo, who knows? But today we're going to talk about designing delightful databases. So what is a database? Well, simply stated, it's a collection of organized data. Now, you might also use the term database to actually refer to the database management software that you tend to work with. And those can be things like SQLite, Postgres, MySQL, Oracle, Microsoft SQL Server, Firebird, Microsoft Access. The list here goes on and on. I could probably spend an hour just naming database management systems. But there's quite a bit. The terms tend to be used independently. You often refer to Postgres as the database you're using instead of the database management system, and that's okay. But for this particular webinar, database is primarily going to be talked about as the structure of the database. And what is in the structure of a database? Well, the primary thing that's in database are tables. So we're going to spend some time talking about those. So a table is a collection of related data. When you're creating your tables, it's very important to have a naming standard for them. So this is an example of what a customer table might look like. And this is a general technique that is pretty common for when you're designing your database tables, to just draw them in a little box like this with the table name right at the top. Now you'll notice I called this customer singular. Some people like to use plural for the name of their table, so they might call it customers. Which is fine, but the important thing is to be consistent when you're designing your database tables, so you don't end up with one table called customers, another one called product. That can get confusing. It begins to get hard to remember which tables have the suffix and which don't. Other people like to use naming standards where they'll add prefixes or other suffixes to tables to make it very clear that they're a table. So I've seen people use TBL underscore and then a name of the table. And again, it doesn't matter what you call your tables as long as you're within the naming conventions that your database system allows and that you use the same names consistent throughout. Now you'll see this customer table has under the name customer a bunch of other names, and these are what's called the columns. So let's talk a little bit about that. The columns describe the specific data that the table can contain. So table being the name of the collection, the columns are the specific pieces of information. And this table data is stored in rows. So you get a table, it has a bunch of columns containing information, and there's multiple rows in a table, each that can have different information because it'll have different data in each of the columns. The primary key of the table is a special column that is used to identify a specific row in the table. It's very important to have a primary key, so you should always have one. Some database systems will let you create a table and not actually assign a primary key to it. SQLite in particular is a little lenient regarding that. I always recommend that you create a very specific primary key for your table so you know exactly how to get at specific rows in the table. I also prefer to have artificial primary keys. So here's an example of a table with what's called some sample data. And you can see it's laid out a little bit differently, almost like a spreadsheet type design here, where each of the columns are the headers at the top, and each of the rows here are the specific data. And you can see the first column is called ID, and that's the primary key. Now, primary keys can be called anything and can contain pretty much anything, but most database systems will give you a mechanism to have a primary key that is automatically populated as you add rows to the table using some mechanism in the database. This particular example probably is something from SQLite, and the first column would be something called an auto increment key. And each time a new row is inserted, the key gets incremented automatically by the database, so you're ensured that it's always unique and it's populated for you. I tend to always use the column name ID for my primary keys, but again, there's nothing specific you have to choose. You just want to be consistent in your naming. The other columns here are just specific pieces of data that are related to this customer table, names, address, that sort of thing. Now you could, and you might think, well, I don't need to have this artificial ID column as my primary key. I could just create a primary key using, say, the last name column. Well, that obviously would be a bad idea because lots of people share the same last name. So that won't give you a unique way to find a particular row in the table. Now, it is possible to create primary keys that consist of multiple columns combined together. So then you might say, well, I'll just create a primary key that consists of first name and last name combined. But that also has the same unique problem. Lots of people have the same first name and last name. And generally speaking, you almost always run into some situation where if you try to use actual user data as your primary key, you're going to run into a situation where it's possible it might not be unique. And then you run into some database issues where you're either unable to store the data or other things, changing names or something like that becomes more complicated than it might otherwise be. So I just say avoid all that hassle, put an artificial key on your tables. Now each of these columns has different types of data in them, and you can control that using data types, much like you can with a programming language. Now the data types that are available vary greatly depending on which database system you're using. Here's some common ones: string, text, varchar. Those three are kind of synonyms for storing any sort of text data in a column. Number, integer, float, decimal, again, various ways to store numerical data in a column. Date and time, sometimes there's a combined one called date time for storing date-related information. Booleans, blob, it stands for binary large object. That can be used for storing things like pictures or files right in a database table column. And I'm sure, depending on the database you're working with, there are other types available to you as well. Now, the other thing to note is that most database systems have very strict type checking. So if you create a column and you tell it that it is of type integer, you can't try to store some text in it. You get back an error from the database system that'll say, well, who knows what it'll say, it'll depend on the system, but it'll be an error of some kind that says invalid. And that's generally what you want. But then if you do work with SQLite, and if you're using Xojo, SQLite is a very popular choice for using as a database. You want to know that SQLite does not care about types in this manner. In SQLite, you could most definitely declare a column as type integer and stick my name, Paul, as text in that column, and SQLite would not complain at all. Now, if your code is structured properly, that sort of thing probably wouldn't happen by accident, but it is just something to consider. It's very different than how most other database systems work, and I do like to point it out as a little possible gotcha to be aware of. Now, when you're designing your tables and your columns or whatnot, you might remember at the beginning we said that a database itself is a collection of related data. So you have to manage these relationships between all the data you're storing. And this is done because the tables can be related to each other. This is what is the essence of a relational database. And the tables can be connected in some manner. And this is done using foreign keys. Typically, the foreign keys also have a constraint on them, which will prevent you from creating data in your database that is out of sync. And you connect up the tables using a concept called joins. And there are a couple different kinds. There's inner joins. There's outer joins. We'll look at those in a moment. And there's different types of relationships between the tables. Tables can have a one-to-one relationship where one row in one table matches to one row in another table. They can have a one-to-many relationship where one row in one table will match to a bunch of rows in another table. And then there can be a many-to-many relationship where rows in two tables can connect all kinds of ways to each other. So first, let's talk a little bit about joins. I mentioned there's an inner join. An inner join, when you connect two tables together, essentially gives you the data that is in both tables. So if you get a little picture here, you can see where the circles intersect is the data you get back if you did an inner join on your tables. Now, this is done using a select statement in the language of your database system. The select command is the command that's used to query the database and pull the data out of the database into whatever tool you happen to be using. So you can display it to the user or process it or do whatever you need. So an inner join gives you the data that's in both tables. It's a very common type of join. There's also an outer join that's broken into two different forms. The left outer join, which gives you all the data in the first table plus data in the second table in this particular manner. And then you've got the right outer join, which is kind of the opposite. All right. So now we're going to talk a little bit about relationships in the database. Now, the simplest one to start with is the one-to-one relationship. This is a direct relationship. It's not used that often because, realistically speaking, there's not a lot of reasons you would want to split your table in this manner if the relationship is this direct. But it's sometimes used to segregate data for performance. I've seen this done if you are using blobs, which you remember are binary large objects. If you are storing these sort of things in the database itself, so maybe pictures, it sometimes can improve performance by having a separate table whose only job is to store these blobs. And then when you need access to them, you join this separate table into the main table and get the pictures out of it. But for other queries where you don't really care about the pictures and you just want to query the information, maybe search or something like that, by not joining in the table that contains all this usually large amount of data, you can improve the performance. So this is more of an optimization technique, but that is where I've seen these particular things used the most. All right, and I got a picture here, that's right. So you can see this particular design here, where there'd be a photo table that contains, say, a picture of the customer, but it's segregated so that all your other uses of the customer table that don't care about the picture don't have to pull in any performance or any penalties related to loading in all that binary data which could perhaps be large. One-to-many is probably the most common type of relationship that you see. And this is where a parent may have one or more children. And the child can only have one parent. So you can see an example of this here. We have a team table, we have a player table. And the team table has some columns, name of the team, the coach, the city they're in. And there's a player table that also has some columns, the name of the player, the position they play, and their uniform number. And you'll see there's a little line drawn between the two tables, and that line is a specific way to indicate the type of relationship. Now the direct one just had a single line. It's pretty simple, but this one you'll notice on the player side there's a couple extra lines branching off at the end. Those are sometimes referred to as the crow feet. And those indicate that it's a many relationship. So you would read that as a team can have one or more players, if you were reading it left to right. And if you're reading it right to left, you would read it as a player can be on one team, because the line on the left does not have the crow's feet. So it only indicates one relationship. So that's how you read that sort of design. This is a very handy design when you're sketching out things on whiteboards or papers to just get a feel for how your database is going to relate to each other, and gives you an idea how you might start to write your queries. Now, when you implement that design, you actually have to add an extra column to the player table. So the team table here, the team table also has had its primary key added. When you're sketching out your designs, you don't often write out the primary key because that's implied. But when you do come time to implement your designs, you are going to need to put in all the details. So the team table here has added to it a primary key ID, and the player table has added to it an extra column called team ID that's marked as a foreign key. And you'll notice with my naming convention I have here, it makes it really obvious what things refer to. So when you look at the player table and you see a column called team ID, well, in my naming convention, I know that columns that end in ID are keys. And I know this one being prefixed with a name is going to be the name of the key where I can find that, the name of the table where I can find that key. So the column called team ID tells me it's a foreign key to the team table. And then you can join this data together using a select statement, something like this, where you're selecting the specific column names from the team table and you're joining it to the player table, and it's doing an inner join on the two key columns, so the primary key to the foreign key. And this would give you back a grouped list or a list of all the teams and every player on each team. All right, moving on to, maybe if I can get this to click, there we go. Many-to-many relationship. And this is where a parent may have one or more children, but the child may have one or more parents. So you end up with something that, when you're designing, looks like this. It has the crow's feet on both ends. And you can read this as follows. So from left to right, you can say an invoice can consist of one or more products, and a product can be on one or more invoices. Now, this is a pretty common example. I mean, if you think about it, it makes sense. I mean, if you're generating invoices to sell things, you're going to generally sell the things more than once. So you're going to allow a specific product to be sold multiple times. And you're also certainly going to allow a specific invoice to sell more than one thing at a time. So that's how this particular thing ends up looking when it's designed. But to implement this, you have to split it up a little bit, as databases don't really have support for this sort of thing built in. And you split it up by having kind of a middle table that acts as the connection between the two tables. So you can see here, the invoice table has just been had its primary key added. Same with the product table. But there's a new table called invoice product. And again, a naming convention is common to use the names of each of the tables combined together for your many-to-many table name. And this invoice product table has on it the foreign keys to the invoice table and to the product table. And I've also added in this particular case another column that's specific to the relationship, which is the quantity. So it tells you, well, how much of a specific product was ordered for that invoice. Now, you obviously couldn't have put that quantity anywhere else. We couldn't put it on the product table because that just wouldn't make any sense. The product could be on any invoice, so the quantity wouldn't apply to all the invoices. It has to apply to a specific invoice. We can't put the quantity on the invoice because the invoice can have multiple products, and you wouldn't want the quantity to apply to every product that's on the invoice. So the quantity actually goes on the specific invoice product. And that's how you design and implement that particular technique. All right, just checking the timing here. And what do we have next? All right, we'll do the next one before we go to our polls. So our next topic is called normalization. Now, these are steps to ensure that you have an efficiently designed database. Now, everyone has seen a database that can be termed not efficiently designed, and these are commonly, from what I see, are databases that are designed over time and just get things added to them without a lot of thought after the fact. Sometimes these are things that are converted from like an Excel spreadsheet or maybe even an Access database that were created by someone that doesn't have a lot of database experience, and they were just directly translated into a full-blown application using a full-blown database system without maybe correcting the design issues. So you can apply normalization techniques to a database design to ensure that you don't have essentially duplicate data is probably the big thing to worry about, because that can make it really hard to ensure that your data, you have good data integrity, that you don't have customers in your database where there's multiple phone numbers that have to be updated when their phone number changes, for instance, things like that. And there's lots of levels of normalization. We're only going to talk about 3 today. First one is called, I wrote here 1NF, that is generally said as one normal form, and it means no repetitive or duplicating columns. Then second normal form is no duplicate data in multiple rows. And third normal form is no columns that are not dependent on the primary key. So let's look at each of these in a little bit more detail. So first normal form is no repeating or duplicating columns. So take a look at this table design here. We have a table called team, and we got some columns, and we got our team name, coach, the city the team is in. And then over time, maybe it became obvious that, well, teams have more than one coach. Well, they can have 2 coaches. Well, we'll add coach 2. And then a couple of years later, oh, well, now they're up to 4 coaches. So you just keep adding these coach columns. And, where does it end? Now in the case of a team, there's obviously a practical limit on the number of coaches, but these sort of things, it's not a great design to have your extra columns just to store information like this. So the way you would normalize it is to start to move this essentially repeating or duplicating data out into its own table. So you would design it by removing those columns from the team table and adding them to a coach table and using our one-to-many relationship to say that a team may have one or more coaches. And our coach table has a name of the coach, and for even more flexibility, you can put a type on this so that you could indicate, if they're the head coach or the assistant coach or the batting coach or whatever it is. And then when you implement it, it uses the same techniques as before to add in the keys and the foreign key. Now, second normal form means that you've achieved first normal form for your database. Plus, you no longer have duplicate data in multiple rows. Now, this particular table here has sample data being displayed. So you can see the names of the coaches and the types and the team ID they refer to. And you can see here the types are repeated. Head for head coach is used in multiple places. Now this specific type of table that I'm doing here, I'm getting a little pedantic with normalization here. For something where this is that specific, it may be okay to have the term head used in multiple places. But this becomes more of a problem when you've got actual, more sophisticated table designs, if you will. And we'll talk a little bit about when it's okay to not be quite as normalized in a bit. But so this is how you could split this sort of thing up. And again, it involves creating another table. So the coach table would have a foreign key into a coach type table that would have the types listed. Now, there is benefits to splitting things out like this. So if you did need to rename the type from head coach to manager or something like that, when you have your data all isolated into its own single table, you only have one place to go in your database to make the change. But if this is scattered all over the place, you could have many, many rows to update in multiple tables. So, it's always a balance when you're designing your stuff to figure out what's going to make the most sense. But this sort of thing, when you go through the normalization process, does ensure that you've got very clean design that doesn't have repetitive and duplicating data. All right, the last one we're going to talk about for normalization is third normal form. And that means you've achieved first and second normal forms. Plus, you no longer have any columns that are not dependent on the primary key. So here is our team table again. And you see there's a column here at the end called coach count. And it's just an integer. Well, how does that get set? Is it every time that the user adds a coach to the team, you increment this integer? Well, that certainly is probably a recipe for some bugs to happen where the count gets out of sync with actually how many actual coaches are available. So instead, you should yank that sort of stuff right off the table and not even have it. And then calculate it as it's needed. So in this particular case, you can just count the number of coaches that are actually related to the team from the coach table. This sort of thing you'll often see for storing totals for dollar amounts and things like that, where sometimes they're hard-coded on a table and perhaps shouldn't be. And like I said, this is sort of thing that also eliminates data integrity issues. You don't want to have a database where on the team table it says coach count equals 5, but then when you select the actual coaches from the coach table, there's only 3. You don't want that. That's bad data somewhere. So now you have to decide, all right, well, which is correct? Is the 3 correct because that's what's in the database? Was the 5 correct and somehow some rows got deleted that I don't know about? You got a situation there that's less than ideal. All right, before we jump into our next topic, I'm going to run our fun little polls here. And our first poll is, what type of apps do you create with Xojo? Run these for about 30 seconds or so, give everyone a chance to vote. All right, great. Our next poll is, do you have a Xojo Pro license? If you're not aware, Xojo Pro is our license that includes the ability to create desktop, web, and database apps, all in one package, if you will. All right, moving on. Our next question is, how long have you been using Xojo? All right, and let's see. Next to last question here is, how do you use Xojo? All right, and our last question is our new one I just added here for this database webinar is, what databases do you primarily use? All right, looks like about everyone got that one. Now let's bring up the results. I think people should be able to see maybe the results for that. We have to close the slides here. So it seems like if you can all see the results, SQLite is used the most common, and then other comes in at second place, which unfortunately doesn't let us be very specific. Certainly, if you do use other databases that weren't in this list, I'd love to hear about that. So shoot me an email. Let me know what it is you work with. All right, let us continue. So next thing we want to talk about is optimization. All right, well, the first thing to do when you're optimizing is to think about indexing. Now, indexing is a specific thing you can add to one or more columns of your tables. And much like an index in a book or anything else, it gives the database system a faster way to find the data that's in the table. And it's particularly useful in conjunction with a where clause. So if you're writing a select statement and your where clause is querying specific columns for information, if you have an index on the columns that are used in the where clause, it allows the database system to search the tables more efficiently. If there weren't an index, how would you expect the database to find rows? It would have to go through them one at a time, looking at the specific column. Now, for small tables, that's perfectly fine, very speedy. But I've worked on databases that have millions and millions of rows in their tables. And it can take a long time to scan those one at a time. But by building an index, you get to have the database system look in the index and say, okay, I found the subset of rows I need right here in this index. I can just yank those out of the table very quickly and send those back. So adding indexing can be a great way to speed up retrieval of data from the database. But you do have to be a bit careful with adding the indexes. Certainly don't just go, well, just to be safe, I'm going to add indexing to every column in all my tables, and then bam, I'm covered. As indexing does have overhead costs. There is storage space required to save all this indexing information. Each time you add data to a table, the index has to be updated in addition to updating the table. That's a little bit of a performance hit. So there are those things to keep in mind. So you really only want to index what makes absolute sense for how your queries and your database needs to work. Now, another way you can optimize is to surprisingly remove normalization. As we were going through our normalization, you notice we were adding more things to the database, more tables generally. This means you're going to have to do more lookups to get at this data that is now spread across multiple tables, where it before was probably in just maybe a single table. So you remove normalization, you can simplify your database access. Now you do, like I mentioned before, you run the risk of having data integrity problems because you're probably going to have essentially duplicate data. But it can be a way to optimize your database depending on the needs. I've seen this used a lot with reporting. Sometimes it can make sense to have a set of tables that are specifically designed to make reporting fast. And these tables could be completely denormalized and perhaps even not representative of live data, but maybe updated periodically throughout the day. So those are some things to consider. Again, this sort of stuff makes sense when you're dealing with large volumes of data. Smaller chunks of data really aren't going to have any sort of measurable difference, but it can make a significant difference when you're dealing with large data. All right, another thing to do is always remember to database maintenance. Now, if you're using a large system like Oracle or Microsoft SQL Server or Postgres or even MySQL, it's possible you actually have a database administrator that handles some of this stuff for you. But if not, or you're using something like SQLite or whatnot, it can be important to make sure that you run periodic maintenance on the database so it can stay running as efficiently as possible. So what does that mean? Well, the big one that's on all databases is a way to analyze the tables and the indexing. And this updates the behind-the-scenes structures that the database uses to look up things. And these structures change over time as rows are added and removed to the various tables. And although they're constantly updated, they can get corrupted like anything else. They can get very large. As they're built over time, maybe they're not built as efficiently as if you told the database, hey, why don't you just toss what you have and recreate new ones from scratch using the current data that's in the database. So that can be a valuable task to do periodically. SQLite and maybe some other databases, but I primarily have seen with SQLite, have a command called vacuum, which tells SQLite to essentially go through and toss out stuff it no longer needs. Its primary effect being able to reduce the size of the SQLite database file. Because for performance, when you delete rows from a table with SQLite, it doesn't actually remove the data from the file. It just marks them as removed from the table. But if you issue the vacuum command, the items that were deleted are actually removed from the file, thus reducing the size of the file. So that can be very handy if your database is used as like a file format or you need to transfer it or anything like that. All right. Now we'll talk about a few different things in addition to tables that you can actually have in your database system. And one of these are called views. And views are a display of data from one or more tables. They can be a way to display calculated data. And essentially, they're a shortcut to a select statement. And with most databases I've worked with, creating a view is simply something along the lines of create view as, and then you type in a select statement. And then instead of having to type that select statement over and over, you can just use the view name, almost like an alias to a select statement, if you will. Views are typically read-only, although some databases, I seem to recall maybe Oracle, probably some other ones, but I do recall Oracle had some way to create views that you could write to. But that's not super common. They are typically read-only. And yeah, here's a syntax for how you often create a view. And you can see here, this is just doing a select statement and counting up coaches. Another thing you can add to your database are something called triggers. And this is code that runs when a database action occurs. And this can be an insert or an update or a delete on a table. And some uses for triggers are for logging purposes. Say you want to have a log table that you want to always be updated when anything in a specific table changes. You know, if you're doing anything that's money related, maybe you want to do that. Who knows? But you may have a logging table. Well, you could have your app write to the log table. But when you're dealing with database systems that are on servers, it is possible for people to access the servers outside of an app. Or maybe they have multiple apps that can access the data that's on the database server. So if you put the trigger in charge of doing the logging, then you don't have to put logging code in a desktop app, a web app, a mobile app, that sort of thing. It can all be just done on the database itself. Triggers can also be used to calculate denormalized data. So for example, on our team table, if we decided we needed to keep the coach count column, we could have a trigger on the insert, update, and delete of that of the coach table. And anytime that table is modified, we could tell it, hey, make sure you set the coach count column on the team table so it is accurate. And then you don't, again, have to worry about putting that sort of code in your application or in multiple applications. The next thing is store procedures. And this is also code that runs on the database server, but these are, as you might guess, they're procedures. They're often not really object-oriented or anything like that. They're just big blocks of code that run on the database server. They're always written in a database-specific programming language, so they're not transferable whatsoever. If you've written a store procedure in MySQL, it's not going to run on Oracle. It's going to be completely different syntax and techniques and whatnot. So some people try to shy away from store procedures for that reason, because it does make moving your data across databases more challenging. But if you know you're tied to a specific database system and the odds of moving are pretty low, you can get some pretty good advantages from store procedures from a performance standpoint, particularly if you're processing data. It can be very speedy to have the server do all the processing and not transfer data from the server down to a client app, have the client app do processing, send the changes back to the server. That network traffic can add up. So store procedures can be very speedy and reduce network traffic, as I just said. They can also be used as a way to encapsulate business logic. Again, if you're building something that has multiple clients, a desktop, web app, mobile app, specific business logic could be encapsulated into a store procedure that's running on the database server so that you don't have to repeat that sort of thing in multiple places. All right, the next thing to talk about is multi-user and concurrency. Now, when you're creating database apps and you're using a database server, well, that generally means that more than one person can connect to the database server at one time. So how do you deal with the situation where two people want to make changes to the same data in the database? Well, you can lock things. This is often called pessimistic concurrency control. And this means the data cannot be modified while it's locked. How you lock the data varies, again, depending on the database system you use. But generally speaking, you would probably lock a specific row that the user has asked to edit. That row becomes marked as locked. And if another user comes in and says, hey, I want to edit this row, they would get an error back from the database system that says it is locked. If generally when you use this technique, you're stuck until the row is unlocked. So it's a little risky if you're using it with something that has a user interface. So the typical situation where this can be a problem is you've implemented this type of locking. So user goes in to edit a customer record and starts editing it and then decides to leave for lunch. And while they're gone, they didn't save or anything, so the record remains in a locked state. Then, of course, the customer calls, well, this person's at lunch. Someone else tries to open the record to make a change and can't because the first user has it locked. Some databases will be helpful and maybe tell you which user has it locked so you can track them down. Some might even provide a way to override the lock, but that's obviously not really a great behavior to do. So that is just one particular use case where you have to be careful about using this type of locking. The other technique is to use optimistic concurrency control, which is essentially no locking. And instead, you check if the row was changed before you attempt to update it. This is commonly done using a timestamp of some sort. And the way this sort of thing would work is the first user would open up the customer record, be editing stuff on the client, not save anything, and then leave for lunch. Customer calls, someone else opens up the record. It's not locked, so they can open up the record, they can make the change they need, and they can save it. The first person comes back from lunch, goes back to editing, and hits the save button. Well, when they hit the save button, the timestamp is compared with the original timestamp from when they opened it and the current timestamp that's on the database. Well, the timestamp on the database is going to be newer now because while this person was at lunch, someone made a change. So that tells the app, hey, there's a problem here. So generally we put up a message that says something along the lines of you need to refresh or something that indicates there's a bit of an inconsistency here that we need to resolve. And it's possible that the data could still be saved if maybe they only changed a column that the other person hadn't changed. You can get pretty involved in how you implement that. But that's how that technique generally works. All right, let's talk a little bit about some Xojo tips when working with databases. Perhaps the most important one is to stay away from using record sets as your app data storage. Record sets are ways to access the data in the database and yank it out for your app to use. But using the record set itself as data storage is not really the best way to go about it. And the reasons for that include that not all databases provide great ways to iterate through a record set. You don't necessarily know how they send the data from the database back to your Xojo app. It's possible that data is cached. It's possible that a bunch of data is sent over the network. It's possible that it's only retrieved when requested. Not all database systems will let you go backwards in a record set. So if you need to iterate or more dynamically find things, that's not going to be a great way to do it. So it's better to just pull the data out into your own data structures. Dictionaries work great for this. Yank out your data from the record set, stuff what you want into a dictionary using the key of the row as the key to the dictionary. Makes it very fast and easy to save and look up things. Generally, you want to avoid using select star when you're writing your SQL select statements, and instead list the specific columns that you actually want. And this again varies depending on the database and what you're dealing with, but select star means send me back all the columns. And if you only need the name to show the name on the screen, well, don't ask for all 50 columns that are on the table and have all that extra network traffic. Just ask for the column you want. Use prepared statements in your Xojo code. This simplifies some of the string concatenation you'll have to do. That's always good, makes your code a little more readable. It also is a security thing by pretty much eliminating SQL injection, which is a little bit of a hacking technique where people can type in database SQL code in a field prompt and get your app to construct it as an actual SQL statement to send to the database to maybe do something bad. By using a prepared statement, you avoid that situation because you're not doing generic string concatenation. And of course, the number one thing to be doing is to always check for database errors after anything that touches the database. After an SQL select, check for a database error. It's possible you made a typo in your select statement. If database error comes back as false, you can get the error message and display it, show it, log it, whatever you want. But that'll tell you what the problem is. So if you did make a typo in a select statement, this will tell you, hey, you got a typo in your select statement, and probably give you pretty good pointer as to where in the select statement the problem is. So it's very important to check for your database errors. Don't just run your code and then when it stops running for some random reason, be completely confused and not understand why. By checking your errors, you'll know exactly what happened. All right, another thing you can use with Xojo, and pretty much any language in one way or another, is something called Object-Relational Mapping. And this is a way to map your tables to classes. So rather than writing a bunch of SQL statements in your apps, you have classes that are essentially in some way linked directly to database tables, and you just interact with the classes in your application. It can simplify things. So essentially each row of a table becomes an instance of a class. Each column is a class property, for example. Calculated fields can be right on the class. They don't even need to exist in the database at all. And actions can be right on the class as well, such as, say, something like save. So it allows you to write code that looks something like this. So if team here is being treated as a class in your code, but if team is directly related to a table in the database called team, then this code would end up with a new row added to that table with the name set to Red Sox. So that can be a lot easier for people to work with than dealing with SQL and all that other stuff. Now with Xojo, there are a couple third-party projects you can grab that will give you some ability to do ORM. And the first one is Active Record from Bikini Software. And then I just this morning put up Storm on GitHub, which you can also grab, and that is another alternative open source ORM software. I've been using this one for years myself. This is not a Xojo thing. It's my own little project I had, so I put it up for people to use. So feel free to try it out. The docs are not online yet, but I'll get those soon. All right, and that takes me to the end. So let's do a time check here. Hey, pretty close. Got a few minutes for any questions. Let me check the question list. All right. Well, there's a couple comments that said that last database poll question should have been multiple choice. I thought it was supposed to be multiple choice. I am sorry if it wasn't. Instead, it ended up being what is your primarily used database, I guess. And Justin is noting that Valentina can be another popular database choice. And Justin also notes on as a tip for connecting to databases, always tries to use SSL for your database connections whenever you can. And that gives you secure database connections so that people can't sniff the data going back and forth over the network. And Justin asks, for performance of accessing image files, would you recommend storing images in a blob or local files? That's a great question. There's two sides to that coin. Some people are going to say, well, always store your large files as files. That's what the file system's optimized for, which would mean the file system on the server so that you can access them from everywhere. And others say, hey, these databases are big and powerful. You can store them in the database and it can handle it. So it's probably going to depend a bit on, which database system you're working with. If you were using SQLite, I probably wouldn't put binary data in the SQLite file. I mean, SQLite itself is a file, and then sticking a file in a file, that has to be less efficient than just referencing files stored on the file system. But if you're dealing with, one of the heavyweight databases like Oracle or Microsoft SQL Server or something like that, I'm sure they're very well optimized to be able to put file type data, such as images, right within the database itself. And Arthur has excellent points as well that I didn't have a slide for, but always have database backups. And that applies to everything, of course, but databases are no exception, and considering what you could possibly have in them being very valuable, should definitely be backed up. And as with any backup, always test your backups, make sure you can restore them on other systems, and make sure everything's working. Great advice. Thank you, Arthur. All right. Well, that's all I see for questions today. There is a database channel in our forum, so certainly head over there when you want to discuss or have database-related questions. Do head on over to Xojo.com and grab release 2.1, which came out earlier today. And stay tuned for upcoming webinars for the rest of August and September. Thanks, everyone, for attending this week's webinar. Have a great rest of your day.